Okay, so if you're watching today, it's 1:15. Some people are absent today, so you might have to see this video. Yesterday, we talked about the three different kinds of conservation momentum scenarios. I even gave you some equations for those. Today, what I'd like to do is I'd like to show you how to apply those to a few examples, and then we're going to look at also inelastic and elastic collisions. All right, so we have a defensive back. It's traveling at 4 meters per second, collides midair with a 75 kilogram receiver. They jump vertically. Why is it important that they're vertical, that they're off the ground? We need to have an isolated enclosed system. So the only forces that matter are the collision forces. We want to determine what speed the athletes move after the collision. So let's just draw a little diagram. Here we have a D-back that's traveling, that's 95 kilograms, is traveling at 4 meters per second, and they collide with a receiver. The receiver is less mass, and they're basically stationary. They're midair. They jumped up, caught the ball, and then the defensive back runs into them. They're 75 kilograms, and essentially they're motionless. Now, during the collision, very important part from yesterday is that we can't really describe what happens here. That collision is too hard to describe. Forces and times are difficult to measure. They're complicated, so we use the fact that whatever impulse the defensive back imparts to the receiver imparts the equal but opposite impulse to the D-back, and that means the total impulse rhymes with hero, zero. No change in the system momentum. Afterwards, we see that they're going to combine their masses, so they're sort of stuck together, and they travel with some velocity afterwards. Now, that's just a picture to sort of make sense of what's happening. It's a dynamic process. It's a static picture. So it's just there to sort of show us what's going on. Here's how I'd write the equation for it. Sum of the momentum before the collision is equal to the sum of the momentum after the collision. That's the starting point for any problem involving conservation of momentum. Before the collision, we have the mass of the D-back times the velocity of the D-back before anything. They hit, they stick together, and how I'd write that now is I have the mass of the D-back plus the mass of the receiver multiplied by the final velocity. And really quickly, we can get to an expression for how fast they move afterwards. It is the momentum of the system divided by the mass of the system. And so V final would just be equal to, let's see, mass of the D-back, velocity of the D-back initial, divided by the sum of those masses. Again, plugging in those numbers, we get 95 kilograms times 4 meters per second. Divide that by the sum of those masses. We have two objects now moving. So what is that, 170 kilograms? I believe I did that math right. And I notice the units reduce, which is what I'd like. The mass units of kilograms reduces. So 95 times 4, divide that by 170, and I get a speed of about 2.2 meters per second. So these things would then move with a speed that's less than it was before, but they have the same momentum. So prior to the collision, after the collision, momentum is the same. That's how it solved a hit and stick kind of problem. Raise your hand if you've ever shot a rifle before. Tell me what I'm doing wrong. Let the record show there's about 3 or 4. So for those that haven't watched the video from home, what am I doing wrong with this rifle shot besides the fact that it's just a meter stick? Why? I'm probably afraid of the kick, right? So if I'm doing this here, when I shoot the bullet out of this rifle, it acquires momentum. What must the gun do? Acquire equal but opposite momentum, because this is an isolated system. When I shoot that bullet out, that bullet pushes the rifle back. I might be afraid of the kick, so I hold it out here, and the problem with that is that's gonna make that gun recoil back at a really high speed. So why do you lock it into your shoulder? What's the advantage of that?
Because then the mass of the gun also has the mass of you
Yeah, I'm adding the mass of my body to the system so that when the gun recoils, it doesn't recoil quite as much because there's much more mass there. Now I'm also going to lean into it a little bit. So those of you that are really good shots here, you lean in a little bit, you take that recoil goes in your shoulder. To make this problem be solvable, easier to solve, if you will, I'm going to isolate the rifle. So I'm going to keep it away from my body, and I just want to be able to determine what the recoil speed would be in the event that I just didn't want to hold it in my shoulder. Those of you that have shot rifles before with scopes, have you ever been scoped? Do you know what that means? You know what that means? So being scoped in this case means that you have your eye too close to the scope, and when you shoot, the thing comes back, and it does come back a little bit, and it leaves a nice little imprint right around your eye socket, because it turns out that the size of the scope is about the same as the size of your eye socket, and you do that once because you're like, oh my, and then you know that you hold your eye further back, because that's what happens is it comes back and gets you right around the eye. Never happened to you? You know what I'm talking about, right? All right. So there you go. Let's go ahead and assume that the person is afraid of the recoil and isolates it from their body. All right. So this is an explosion problem. So when I'm doing explosions, usually what that means is that the total momentum before is 0 and the total momentum after is 0. As a little picture, we have the gun, we have the bullet. Bullet's obviously inside the gun. It doesn't look like circles, but once we are all done, the bullet gets shot out this way with a really high speed. The gun recoils this way with a slow speed, but they have the same momentum. And that's because it's an isolated, enclosed system. So how would I go through and solve that? I would write the mass of the bullet multiplied by the velocity of the bullet after the collision, so final. I'm going to use absolute value, would be equal to the mass of the gun multiplied by the velocity of the gun after the explosion, or after the shot. I'm just using absolute values because I don't care that it's opposite direction. I just want to know how fast it recoils. So, velocity of the gun. It's really just a ratio of the masses multiplied by the velocity of that bullet that's being fired. I'm going to make a mistake intentionally, and you tell me where my mistake is. Okay, I made a mistake intentionally so that you don't make this mistake on the quiz or test or exam or anything like that. What's the mistake that I made? I have to have the same units there. If I don't have the same units, it becomes gram meter per second per kilogram, and it becomes meaningless. So I'm going to change one of these things. How about I just make that be, for me, I might make this be 2,500 grams. It's just easier for me to work with bigger numbers and smaller numbers. So I'm going to go ahead and convert the 2.5 kilograms to 2,500 grams. Now I get the cancellation that I need. And if memory serves, last hour, I got that as a speed. Does anyone confirm you get about 13 meters per second? There we go. If the system were isolated, enclosed, that would be the recoil speed of that gun. Okay. Now, that's all I had planned for yesterday, but I just ran out of time. Poor time management. So what I'd like to do today is I'd like to try to continue with this lesson by looking at how we can classify collisions as either elastic or inelastic. I think the fact that we had the happy sad balls out from before, you guys might remember the happy sad balls. One was highly elastic, the other one was inelastic. Momentum is always conserved because forces always act through the same amount of time. But those in which kinetic energy are conserved are called elastic. Those in which our kinetic energy is not conserved are inelastic. So whether or not things are elastic or inelastic depends on the degree of elasticity, how much kinetic energy we have conserved. Now the pictures on the left show two billiard balls coming in, approaching each other. If they had equal masses, could you tell that person that you're sitting next to what is the momentum of the system prior to the collision? You guys agree it's 0? Before the collision, equal masses, it looks like their velocities are the same, so before the collision, momentum is 0. After the collision, if the collision is elastic, do you guys notice that they still have 0 momentum? Yeah, momentum includes direction. So they recoil with 0 momentum total because we have to consider the direction there. Can you tell also that the kinetic energy is the same? There's no overall loss of speeds. The speeds are still the same as they were before. Look what happens if they're inelastic. If they're inelastic, would you agree they still have 0 total momentum? Still have 0. But the amount of kinetic energy is quite a bit reduced. Remember, kinetic energy is proportional to the square of the speed. The speed has dropped down a lot, so we lost a lot of kinetic energy there. Where did it go? These collisions put a lot of energy into heat. So where that energy goes is into heat. So whether or not things are elastic or inelastic depends on the amount of kinetic energy that's conserved. Total energy always conserved. Wherever that energy goes, the kinetic energy is turned into internal energy when objects deform. So this is about whether or not we conserve kinetic energy. Okay, let's take a look at just a problem or two. A truck traveling east collides with a car traveling west. It's perfectly inelastic. What that means is that they hit and they stick together. I'm going to give you some exam questions right now, ahead of time. Try this, a little bit of review. During this collision, the object that experiences the bigger force, the truck or the car, which one collides with a greater amount of force? Tell that person that you're sitting next to what you think the answer is to that one. It's a review from stuff that we covered this semester. Which one experiences the bigger F? Either one. Big truck traveling fast, lots of momentum. Little car traveling slow, little momentum. Which one experiences the bigger force of collision? The same. Which law are you relying on? Third law. Forces always come in pairs, equal but opposite. So when they hit, forces are the same. Which one experiences the bigger change in velocity? During the collision, they're going to change their motion. Which one experiences the bigger change in their motion? Go ahead, try it. Yeah, well, do they stop necessarily? They don't necessarily. They're going to travel in the direction of whichever one has the bigger momentum. If they had equal momentum, they'd come to a stop. But are you guys in agreement here that the truck has a lot more momentum than the car?
Yeah. But I feel like that car is going to have a larger change in velocity because it's going to get completely turned around by the truck.
Can we support that through some, instead of your gut, I want you to support that with some laws that we've studied this year.
The truck has more kinetic energy because its mass and velocity are.
Okay, it definitely has more kinetic energy.
That's it.
Okay, I appreciate it. What I'm trying to do is your gut is right. It's the car is gonna experience a bigger change in velocity. What I was looking for is supporting through some sort of laws that we talked about this year. I would just look at it from a standpoint of mass. The truck's mass protects its motion. It's not going to change its motion as much because its mass is sort of like a protector. If you wanted to go F equals m times a, since the mass of the truck is bigger, its acceleration will be smaller. And acceleration is related to change in velocity. Do you guys agree the contact time is the same? So the delta V over T, the T is going to be the same. It's really the delta V it's going to be much bigger for the car. If you're in a small car versus a big truck and you get into a collision, the small car is going to experience the bigger delta V. How about this one? Which one experiences a bigger change in momentum? Brand new topic. The first two was Newton's laws, F equals m times a, and Newton's third law. What about this one? Which one experiences the bigger delta P? Should be the same. And the reason for that is that whatever impulse the truck imparts to the car has to impart an equal but opposite impulse to the truck. Their delta P should be the same. Otherwise, we can't use conservation laws. To be conserved means that what we start with is what we end with. So any change has to be offset by an equal but opposite change. So each car has to have the same delta P. So this would be equal, this would be equal, this would be the car. None of those require math. Those are all concept stuff. And what kids mostly struggle with in a physics class is the concepts. Okay, that's been my history on that. Okay, what is the velocity of the two cars immediately after the impact? This would be a hit and stick, perfectly inelastic collision. It's really not too bad. I'm going to write it like so. Sum of the momentum before is equal to the sum of the momentum after. Both objects are moving. We can handle that. The mass of the truck times the velocity of the truck initially. I'm going to add to that the mass of the car times the velocity of the car initially. One thing I noticed is that the car is moving in the opposite direction. I'm going to let that go in as a negative sign for the velocity. So when I put in the speed or the velocity for the car, I'm going to have that be negative, just because it's a directional quantity. On the right-hand side, because they hit and they combine, this is perfectly inelastic. That means they hit and they stick together. The mass of the truck plus the mass of the car, they move together with some final velocity. And I mentioned yesterday that most kids find the solutions to the conservation momentum problems to be fairly straightforward once you get the equations written down, but not too bad. Solve that for B final. Okay, let's put in these numbers now. This is 2,800. This is 14 meters per second. Plus, this is 1,400, so it's got half the mass. 1,400 kilograms. And it's traveling in the opposite direction at 7 meters per second. This is where the negative comes in. Which effectively reduces the momentum of the system. If they were traveling in the same direction, then those numbers would add. These are now subtracted because of the difference in directions. And then I divide that by the total mass, which would be 4,200 kilograms. Now you go through, do a bunch of math, and what you get, this would be fine. So I'm doing multiple steps there, sorry. I'm going to divide both sides by the sum of the masses to be able to get V finals equal to that. When you're done, you get about 7 meters per second. Now it's positive, which means that it's pointed in the direction of the truck. If I make an error, and I don't realize that I made an error, and that number comes out to be negative, then that means it's in the opposite direction from what I assumed. Okay? I'm going to show you a couple of car crashes here. I think I have seen some of these things out in the parking lot. Unfortunately, you got the lights on. Now, frontal crash test demonstrating this is an F-150 meeting a Honda Civic. And so now I want you to notice something. Can you guys see the Honda Civic is traveling faster than the truck? Watch their collision here. The test engineers designed these to have the same momentum so that when they collide, they basically come to a stop. Bigger mass, smaller velocity, smaller mass, bigger velocity. You see that when they hit, they both changed the same amount of their momentum. They basically went to zero total momentum. Do you notice how much the velocity of the car changed? The velocity of the car quite a bit changed, whereas the velocity of the truck didn't change as much. Now here's this is one that has, one of these things is like a raised up cab, and so they're obviously concerned from a safety standpoint that the higher up that truck hits the car, you got to be careful with that. You want to make sure that the the passenger portion of that vehicle, people are safe there. But yeah, this is again showing you what happens during those collisions. Do you guys agree with a lot of mechanical energy loss? Yeah, perfectly inelastic collisions where they hit and stick together, typically characterized by huge mechanical energy losses. Where's it going to? Heat, sound, and so forth. So the metal often will get to the point where it actually melts there, and that's just because it's so hot from that collision. Okay. Now, hopefully you guys never get into those kinds of collisions, but in the event that you do, you're protected hopefully from the crumple zones from the car. All right, let's try one more. I wanted to do one last problem here with you guys on a football thing. So it is football season. I tried to find a picture of a running back from the Lions, and I lightened it up so it doesn't use as much toner for you. Can you guys tell who that is? For those of you that are Lions people? It's number 27. I don't know who that is. He was getting kicked in the face, though, apparently. I was trying to do an inelastic collision, a hit and stick. That's all I could really find. So, all right, let's try it. He jumps over the goal line, and he collides with the linebacker going the opposite direction. And it's a hit and stick right in the middle of the air over the goal line. The question is do they go into the end zone or do they go back into the playing field? So you have to be able to determine that based on momentum. Draw a quick little picture. I want you to actually go through and try this one. We'll look at how to determine the last question, which is how much KE is lost after you solve this. Give it a go. And you shouldn't have to do a whole lot of math to determine that the running back scores. It's just about momentum. Just look at the momentum of the running back compared to the momentum of the linebacker, and you see that the product of his mass and velocity is bigger than the mass and velocity of the linebacker. He's going to score. And so if you had a question like this on a test, you wouldn't have to necessarily determine what their final speed was, just determine whether or not he scores. It's based on momentum. Now, you still want to find the speed, because we're going to calculate what the loss of kinetic energy is, right? So he's going to score, and then try to get through that, see if you can do it. The number I'm getting there is 1.04 meters per second is how fast they're going to continue to move into the end zone. And hopefully I did that math right. I did that correct. Did that fifth hour and remember that number. Anyone confirm? Okay. Now, I want to talk a little bit about kinetic energy loss. So how would I quantify the amount of energy loss? A lot of energy went into other forms, and so we want to quantify that. So it's our last topic here. Let's go ahead and do that. Delta KE would be equal to the kinetic energy that we have after the collision. And I'm going to subtract from that the kinetic energy before the collision. The math looks complicated. It's not too bad once you sort of see what all these symbols mean. After the collision, we have both objects moving together. With some final velocity that we just calculated. That's the kinetic energy afterwards. Before the collision, we had two objects moving separately. So I'm going to subtract from that now 1/2 the mass of the running back multiplied by the running back's initial velocity squared. And then I'm going to subtract from that the amount of kinetic energy of the linebacker. It looks complicated. It's just kinetic energy formulas. Let's go ahead and just plug those numbers in for completeness sake. So, will you turn and tell that person that you're sitting next to whether or not the answer I compute here should be positive or negative when I'm all done? What should the answer, should it be positive or negative? You remember kinetic energy is not directional. Kinetic energy is scalar. Is the energy increasing or is it decreasing? I don't know why I did that. It's decreasing. The kinetic energy after the collision is less than it is before the collision, and so what we calculate here should be negative. Let's go ahead and put these numbers in. This is 180 kilograms. They're traveling afterwards at 1.04 meters per second. I have to square that. Subtract from that 1/2 of 75 multiplied by 6 squared. The running back had a lot of kinetic energy. He's moving at 6 meters per second. If I square that, that's going to be a pretty big number. And then I take away from that 1/2 the linebacker's. He was less or more massive, but traveling quite a bit slower. And so his kinetic energy was even less than the running back. Let's just go ahead and plug these numbers in. After the collision, I only have about 97 joules remaining. Before the collision, let's do the before. 0.5 times 75 times 6 squared. The running back had 1,350 joules before he collided, so he's got a lot of energy there. The linebacker, 0.5 times 105 times 2.5 squared, 328 joules. When I'm all done, 97 minus 1350 minus 328, we have a loss of about 1,581 joules. If you've ever been to a football game and you hear the sound that comes from these collisions, that sound is energy loss. The deformation of the shoulder pads and the body, all that kind of stuff, that's all going into non-mechanical energy forms. Ultimately, it turns into heat. That's how to go through and solve that problem. Okay? Folks, I apologize that yesterday I did not get through the quantitative examples of conservation of momentum, which means that the homework might have been a little bit more challenging to do. There's just another problem or two on inelastic and elastic collision. So do your best to get those things done by tomorrow. If you don't, I understand that because there's a lot there. Just do your best with it. I'm going to share answers with those things tomorrow. I have the answers to the review as well. I'll share those with you. and then tomorrow I want to have you work on a lab. Okay, so you'll be working on that, and then whatever time we have remaining to do some review.